In our previous videos, we reviewed aspects of atomic structure and bonding, which was review from general chemistry. Now we're going to start to focus on organic chemistry, starting with a closer look at the structure and shape of organic molecules. This video in particular, we're going to talk about using Lewis structures to represent organic molecules. Now, a common representation of compounds held together by covalent bonds would be Lewis structures. Now, how do we draw Lewis structures? There is a systematic approach that you can take. With experience, you'll be able to draw Lewis structures rather quickly, but I believe it's important to review this systematic approach so that when you come across structures that you're not familiar with, you can always come back to basics. The first step you can use when trying to draw a Lewis structure is to determine the total number of valence electrons. So for example, if we're looking at methane, CH4, we know that carbon has 4 valence electrons and each hydrogen has 1 valence electron. So with 4 of them, that gives us another 4. So we have a total of 8 valence electrons. Step 2, we want to connect our atoms. We have to be careful of different representations. The way that things are written do not always represent the connectivity. So we have to keep in mind aspects of structural theory. We know that carbon likes to form 4 bonds. Hydrogen can only form 1 bond. Oxygen forms 2 bonds. So these are things that we have to look out for. So in the case of CH4, since hydrogen can only have 1 bond, we know that the carbon has to be in the middle, and then the hydrogens have to be connected to the central carbon. Step 3, we can use any extra electrons to form multiple bonds or lone pairs. So any extra electrons can be used for multiple bonds or lone pairs. In this example, we don't have any extra electrons, so we're done with step 3. And step 4, we check the structure. One thing we want to check is that we've used the correct number of valence electrons. And another thing we want to check is that everybody obeys the octet rule. So looking at methane, we know that each line represents a pair of electrons. So this gives us 2, 4, 6, 8 electrons. And we started out with 8 valence electrons. So yes, we've used the correct number of electrons. The second thing to check is about the octet rule. And when we are counting for the octet rule, we think about this pair of electrons counts for carbon and it counts for hydrogen. So carbon has 2, 4, 6, 8 electrons. It has an octet. Hydrogen has 2 electrons. Each hydrogen has 2 electrons. So the hydrogens are also happy. So this is a correct Lewis structure for methane CH4. Let's look at another example, CO2, carbon dioxide. So starting with the total number of valence electrons, carbon has 4 valence electrons and each oxygen has 6, so that gives us a total of 16 valence electrons. Now next up, we can connect our atoms. And there's really a couple ways you can go about this. If you want to go the simplest way, when we connect our atoms, well, let's just guess that carbon is going to be in the middle and our oxygens are going to be on the outside. So OCO is a way to connect the atoms. Next, we can use extra electrons to make up multiple bonds or lone pairs. So you could look at this and think about the fact that, well, I know that carbon likes to form 4 bonds, so maybe I'll make double bonds right away, because now that gives this carbon has 1, 2, 3, 4 bonds, and that gives it the 2, 4, 6, 8 electrons in the octet. But then this oxygen has its 2 bonds, that's good, but when we count for the octet, it only has 2, 4 electrons. So let's use more electrons to give a lone pair and another lone pair. So now oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8, and carbon has 2, 4, 6, 8. So everybody obeys the octet rule. Have we used the correct number of valence electrons? So here we have 2, 4, 6, 8, 10, 12, 14, 16 electrons total. We have 16 valence electrons to work with, so this is a good structure. Another way you might go about this is when you decide on your connectivity and then you add in your extra electrons, maybe you just fill in all lone pairs to give everybody an octet. And then you check. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons, but we're only allowed 16 electrons. We can think about getting rid of 2 lone pairs and making a double bond. And then we can get rid of another 2 lone pairs and make another double bond. And so this brings us right back to the same structure where we have carbon in the center with 4 bonds to the 2 oxygens, 2 lone pairs on each oxygen, and overall we have a valid structure. So I'd like you to keep in mind this systematic approach. As we get more experience, you're going to be able to go through these steps in your head. You're going to combine these steps and do them at the same time. But as long as you have this in mind, whenever you get stuck trying to draw a Lewis structure, you can always go back to basics and go through it slowly, stepwise, and you'll get to your correct structure. Next, let's take a look at a few more examples and let's draw Lewis structures. Now, here is a type of representation. It does give you some information about the connectivity, about the way the atoms are connected to each other, but it's not as simple as just reading left to right. Let's start with this compound, CH3OH. This is methanol. And if we start with the number of valence electrons, we know that carbon has 4 valence electrons. Each hydrogen has 1 valence electron, and we have a total of 4, so that gives us another 4 valence electrons. And then oxygen has 6, so we have 14 valence electrons to work with. Next, in terms of connectivity, although it's written like this, it doesn't mean CHHHOH. We know that this can't be an acceptable connectivity because hydrogen only wants 1 bond, and these hydrogens each have 2 bonds. And we know that carbon likes to form 4 bonds, but here carbon has only 1. So we don't read this exactly from left to right. This is not the correct connectivity. Instead, we'll focus on the non-hydrogen atoms. And so we have carbon connected to oxygen. So we're sort of reading from left to right, but we're skipping some information. We know that carbon is connected to oxygen. Now this carbon is also connected to 3 hydrogens, so we can fill those in. And then this oxygen is connected to 1 hydrogen, so we can fill that in. And now we have our overall connectivity. We've used up 2, 4, 6, 8, 10 electrons, and remember we have 14 valence electrons to work with. We can see that carbon has its octet. We can see that our hydrogens all have the 2 electrons that they need, but oxygen only has 4 electrons, so we need lone pairs. So we're going to add our 2 lone pairs onto oxygen. And now we're ready to check our structure. So carbon and now oxygen both have an octet. Each hydrogen has the duet, or the 2 electrons that it needs to be like a noble gas. And we're using 2, 4, 6, 8, 10, 12, 14 electrons, which is what we have to work with. This is an example of an alcohol. In our next structure, we have 4 carbons, each of which has 4 valence electrons, so that gives us 16 valence electrons from the carbon. We have 10 hydrogens. Each hydrogen has 1 valence electron, so that gives us a total of 10 valence electrons. And then we have 1 oxygen with 6 valence electrons. So this gives us a total of 32 valence electrons. Once again, as we think about connectivity, we want to focus on the non-hydrogen atoms, and we have carbon connected to carbon, oxygen, carbon, carbon. So let's write out that connectivity. So we have carbon, carbon, oxygen, carbon, carbon. The first carbon is connected to 3 hydrogens, and then 2, and then 2, and then 3. So let's fill those in. We have H, 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 2 more H's, 2 more H's, and 3 H's. The oxygen is not connected to a hydrogen, but it must be connected to 2 lone pairs. As we check our structure, we can see that each carbon has an octet. We see that oxygen has an octet, and we see that each hydrogen has the 2 electrons that it needs. In terms of valence electrons, we are using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 valence electrons. So this is a correct Lewis structure for diethyl ether. And in our third example, we have carbon connected to 3 hydrogens. This carbon is also connected to a carbon that's connected to 2 oxygens. And then we have this hydrogen here. So let's figure out what this connectivity is. First of all, let's think of our total number of valence electrons. We have 2 carbons, so that gives us 8 valence electrons. We have 4 hydrogens, which gives us 4 valence electrons. We have 2 oxygens, each of which has 6, so that gives us 12 valence electrons. So that's a total of 24 valence electrons to work with. In terms of connectivity, we have our first carbon. We know it's connected to 3 hydrogens. That first carbon is connected to the second carbon, which is connected to oxygen and another oxygen, and one of those oxygens is connected to a hydrogen. We already have 4 bonds to this carbon. This carbon, we only have 3 bonds, so if we make this a double bond, now carbon has its 4 bonds, this oxygen has its 2 bonds, and this oxygen has its 2 bonds. So the number of bonds looks good and everybody's happy. But the total number of electrons isn't correct yet because we have to add lone pairs for the oxygen. So keep in mind, carbon wants to have 4 bonds, and then it's done because it has its octet. Oxygen likes to form 2 bonds, but that doesn't give it its octet, so it also has to have 2 lone pairs to give it the total of 8 electrons. So double checking the structure, we have an octet for this carbon and for this carbon. We have an octet for both oxygens, and all of our hydrogens are satisfied as well. In terms of the total number of electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24, which matches the number of valence electrons we're allowed to use. So this is the Lewis structure for acetic acid, an example of a carboxylic acid. So with these examples, we have seen a few of the types of structures of organic compounds. We have an alcohol, we have an ether, and we have a carboxylic acid. We're going to learn more about these later this semester and throughout the entire year of organic chemistry. Next, let's look at a few more examples. So here we have a hydrocarbon. We have only carbons and hydrogens. And let's just start with the connectivity. So our first carbon is connected to 2 hydrogens, and it's connected to the second carbon, which is connected to 1 hydrogen. And that second carbon is connected to our third carbon, which is connected to 3 hydrogens. So this carbon has its 4 bonds, it has its octet, but these carbons only have 3 bonds, they don't have an octet. So let's add in another bond so that the first 2 carbons have a double bond. Now this carbon has its 2, 4, 6, 8 electrons. This carbon has 2, 4, 6, 8. And this carbon has 2, 4, 6, 8. And every hydrogen has the 2 electrons that it needs to be like a noble gas. You can also go back and calculate the total number of valence electrons and double check the correct number of valence electrons. But as you keep seeing more and more of these compounds, you're going to be able to draw out the structure much more quickly. This is an example of an alkene where we have a carbon-carbon double bond. Next, as we look at this example, we have a carbon that is connected to a carbon which is connected to another carbon. Our first carbon is connected to one hydrogen, so let's write this on the outside. And then our third carbon is connected to 3 hydrogens. And our central carbon is connected to 0 hydrogens. So what is this going to look like overall? We have enough hydrogens connected here. We have 4 bonds. We don't have any more hydrogens to work with, but these carbons are not happy. They only have 2 bonds when they want to have 4. So this means that between carbon 1 and carbon 2, we must have a triple bond. So the triple bond, this tells us that we have 2, 4, 6 electrons being shared between these 2 carbons. So now this carbon has 4 bonds, it has its octet. This carbon has 4 bonds, it has its octet. This carbon has 4 bonds, it has its octet, and each hydrogen is satisfied as well. This is an example of an alkyne, a hydrocarbon that contains a carbon-carbon triple bond. In our next example, we have CH3CH2CHO. Now notice the CHO, this tells us that this carbon is connected to this hydrogen, and this carbon is also connected to this oxygen. Right? It doesn't mean COH, but instead it is CH and O. So we have our first carbon connected to our second carbon connected to our third carbon. Our first carbon is connected to 3 hydrogens. Our second carbon is connected to 2 hydrogens. And our third carbon is connected to a hydrogen, and it's connected to an oxygen. Our first carbon has 4 bonds, it has its octet. Our second carbon has 4 bonds and its octet. Our third carbon only has 3 bonds, it doesn't have its octet. And our oxygen doesn't have an octet either. So let's make this a double bond. Now our carbon has 4 bonds and it has its octet. Oxygen has 2 bonds, so that part is good, but we still need our lone pairs, so we're going to add in our 2 lone pairs on the oxygen. And now oxygen has its octet. So this is an example of an aldehyde where we have a carbon-oxygen double bond, and that carbon is also connected to a hydrogen. And in our last example, we have CH3COCH3. So if we had our first carbon connected to our second carbon connected to oxygen connected to carbon, this would be a problem because this carbon is connected to 3 hydrogens, but this carbon doesn't have any hydrogens. We can't have multiple bonds between the carbon and the oxygen because oxygen already has its 2 bonds. So this representation can be a little bit misleading until you learn how to read it. And so technically what this means is that this carbon's connected to this carbon is connected to this carbon, and this carbon is also connected to an oxygen. So it's not this, it is this. Carbon, carbon, carbon. The central carbon is connected to oxygen. The carbon on the left is connected to 3 hydrogens. The carbon on the right is connected to 3 hydrogens. So the carbon in the middle, we know that it's connected to an oxygen, but now we also know that it must be connected by a double bond, which will give this carbon the 4 bonds and the oxygen the 2 bonds that they both want. And then finally, we add in the lone pairs, which gives oxygen its octet, and all of the carbons have their octet, and all of the hydrogens have the 2 electrons that they need. Now this compound is an example of a ketone. It has the same C double bond O that we had up here. This is a common structural feature, but this carbon is connected to 2 carbons, so this one is called a ketone. In particular, this is acetone, which is a solvent that you use quite frequently in the organic lab. Next, let's get back to some simpler compounds, and we're going to draw Lewis structures for a few of these. So let's go back to our systematic approach to drawing Lewis structures. Each hydrogen has 1 valence electron, so that gives us 2. Oxygen has 6, so we have 8 valence electrons to work with. Let's add them up for all of them, actually. Here we have 3 hydrogens, and oxygen has 6 valence electrons, but notice we have a positive charge. So a positive charge tells us that we have 1 less electron. So we have to subtract 1. So 3 plus 6 is 9 minus 1. Once again, we have 8 valence electrons. And in our third example, HO minus, hydrogen contributes 1, oxygen contributes 6, but we also have this negative charge, which means we have an extra electron. So this gives us 8 valence electrons as well. When we think about the connectivity, we have oxygen in the middle and hydrogen on either side, and we can fill in our lone pairs. Oxygen has its octet, each hydrogen has its duet, and this structure is using 2, 4, 6, 8 valence electrons, which is what it has to work with. In our next example, we still have to have our oxygen in the middle, and let's connect our 3 hydrogens to it. Oxygen must have a lone pair, and so we've got 2, 4, 6, 8 electrons, which is what we have to work with. And then in our last one, we have H connected to our O. The oxygen must have 3 lone pairs, and now we have our 8 electrons, which is what we're allowed to use. But these structures aren't complete. Notice water is neutral, there's no charge, and our Lewis structure has no charge. That's great. Here, our Lewis structure has no charge, but our compound does have a charge here as well. So we're missing something with these Lewis structures. And what we need to include is formal charge. So formal charge is a type of electron bookkeeping. Okay, the formal charge is the difference between the number of electrons in a neutral atom versus the number of electrons on an atom when it's in a molecule. So in your book, they have a formula to calculate it. I like to think about it as formal charge equals alone minus own. Alone refers to how many valence electrons a particular atom has when it's by itself. In other words, this is what we get from the periodic table. And then own refers to how many electrons a particular atom has in a compound. Now, how do we count these electrons? Well, any lone pair belongs completely to that atom, and then any bond, half of it belongs to that atom. So let's see what this means. If we're looking at this oxygen, on the periodic table, oxygen has 6 valence electrons, right? That's what we said over here. That's what we were using. And in this molecule, oxygen completely owns 2 lone pairs. So it has 2 4 electrons. And then in terms of the bonding pairs, when we're counting for the octet rule, we say that oxygen has both of these electrons. But when we're counting for formal charge, then we think oxygen has 1 of these electrons and hydrogen has 1 of these electrons. So we are counting differently. So oxygen owns 1 of these and 1 of these, both of these, both of these. So in this case, oxygen owns 6, which gives us a formal charge of 0. Hydrogen on the periodic table, it has 1. In this molecule, it has 1, so this has a formal charge of 0. 1 minus 1 equals 0. So the formal charge on each of these is 0, and typically we don't have to show the formal charge when it is 0. In our next example, if we look at the hydrogens, when it's alone, it has 1 electron. In this molecule, it owns 1 electron, so that gives a formal charge of 0. This hydrogen also is 0, and this hydrogen also has a formal charge of 0. But if we look at the oxygen, On the periodic table, oxygen has 6 valence electrons. Now, what does it own in this molecule? It owns these 2 electrons, and then it owns 1 of each pair. So we've got 2, 3, 4, 5 electrons. So 6 minus 5 equals 1. So this oxygen has a formal charge of +1, which is good because that matches the charge on the ion. So we need to indicate the formal charge on the oxygen by including a plus. Now, in some cases, you might see your ion in brackets and the formal charge is indicated on the outside of the brackets. That's not the best way to show it. It is going to be much more useful, and my expectation is that you're going to show the formal charge right on the atom, not vaguely connected to the ion. In our third example, hydrogen on the periodic table has 1. In this molecule, it owns 1, so hydrogen has a formal charge of 0. Oxygen on the periodic table, it has 6 electrons. In this molecule, it owns 2, 4, 6, and it owns 1 of these 2. So that means it owns 7 electrons. So that gives it a charge of -1. So on this oxygen, I'm going to put a negative. And now the sum of formal charges on this ion, so this is -1, this is 0, adds up to the total charge on the ion. So it is important that a Lewis structure must include any non-zero formal charge. Okay, you must draw that explicitly. If you just have what's drawn in black, that is not a correct, not a complete Lewis structure. You must also include the formal charge. I tend to put a circle around my plus or my minus just to make it more clear that I'm really talking about a charge and not just a stray pencil mark. So that's what I'm going to show. When you are writing it, please be clear, especially if you have to erase something. Please make sure it is very clear to the observer whether you're talking about a negative or a positive or whether it's just a stray pencil mark. Being able to show formal charges and really paying attention to formal charges becomes really important as we start to consider reactions.